Selenium is a trace mineral and is essential in human nutrition. There are organic and inorganic forms of selenium, with the organic forms containing either a cysteine or a methionine group. Selenium is found in several food sources, however, Brazil nuts contain the largest concentration of this nutrient. Like with zinc and manganese, selenium is also a component of important antioxidant enzymes. One of the most prominent is glutathione peroxidase, which is involved in the removal of harmful hydrogen peroxide and hydroperoxide compounds. There are several other important endogenous antioxidant enzymes dependent upon selenium, including selenoprotein P, selenoprotein R, and thioredoxin reductase. As we will see with iodine, selenium is also involved in the synthesis of thyroid hormones. Here are the forms of selenium. So you see there are classes of organic and inorganic forms of selenium. We have selenium bound to cysteine and selenium bound to methionine in the selenocysteine and selenomethionine forms. We also see selenium in the free inorganic state, so as selenite, selenate, and selenide. We see that food sources containing selenium typically have selenium in the organic forms as selenocysteine and selenomethionine, and we'll see more detail on these food sources. So foods rich in selenium include Brazil nuts, so this is going to be the richest source of selenium, with only a handful of these Brazil nuts containing the RDA level for selenium. So the daily RDA level can be reached by just having a handful, about 5 to 7 of the Brazil nuts. Also, we see selenium in cereals and grains, seafood, dairy, some other vegetables, and plant-based foods such as garlic and broccoli. However, interestingly, the selenium content found in plant-based foods depends largely on the selenium content in soil. So it will vary significantly. So depending on the amount in the soil will affect the amount of selenium in the plant-based foods. We see the method of absorption for selenium. So the primary absorption site is the duodenum, and there are several mechanisms of absorption. There is one transporter specifically for the seleno amino acids. So selenomethionine and selenocysteine is absorbed through the amino acid transport system. And then we have a mode of absorption that is passive diffusion, and then we have active transport. So we see the different forms being absorbed through each of these mechanisms. So for the active transport, it's selenate. For passive diffusion, it's selenite and selenide, and we'll see that in this diagram here. So here is the diagram of the digestion and absorption of selenium. So we have the primary forms found in foods, which is the organic form, the selenomethionine and selenocysteine, and we can see that these forms are absorbed through this amino acid transporter and then will be circulating still in the organic form in the enterocyte, and then it exits the basolateral membrane in the organic form still bound to the amino acids. We see the organic forms, so the selenite, the selenate, and the selenide. So we'll first look at the selenate here. That is going to be transported across the brush border membrane with this ATPase. So we see this is the selenate, and then it exits the enterocyte. We can also see that it can be converted to selenite. We see that this selenite form is absorbed by passive diffusion and then exits the basolateral membrane. And then we see here the selenide also will enter through the diffusion process and then exit the basolateral membrane. So here are the inorganic forms, and we see that in circulation they are bound to different compounds such as the lipoproteins, including the VLDL or LDL. There is a process of binding, so there are certain binders such as these heavy metals or phytates that will bind selenium and limit its absorption and will promote the excretion through the feces. So now we'll discuss the functions and mechanisms. So primarily we're going to see selenium will be a component of a number of antioxidant enzymes. So these are enzymes that serve an antioxidant role. We see and will primarily focus on the glutathione peroxidase. We've seen the glutathione peroxidase before. We've seen how it has a capacity to aid in the reduction of vitamin C. So it promotes the conversion of vitamin C from the oxidized to the reduced form. So converting it from the dehydroascorbic acid to ascorbic acid. So we see that selenium plays an important role as a component of this glutathione peroxidase. So this is selenium dependent enzyme. We see that it catalyzes the removal of hydrogen peroxide and hydroperoxides from tissue. So we see that that is going to be a big role of the glutathione peroxidase, and we'll see a diagram of this. Selenium availability affects the activity of this enzyme. So we see here the different reactants that will interact with the glutathione. So first hydrogen peroxide or lipid peroxide or organic peroxide will interact with the glutathione in the reduced form, and we see glutathione peroxidase here. So it goes from the reduced to the oxidized form, and we see that the products here then will be water, or so one or two water molecules plus either a hydroxy lipid or a hydroxy form of another organic substance. So we see these are going to be the products of the interaction with glutathione, each of these being reduced to water, and then this additional reactant. So of course glutathione reductase will need to be reduced. So once it interacts with a radical or hydrogen peroxide, it will need to be reduced itself. So you see that NADPH, actually, so the NADPH plus H plus will actually interact with the oxidized glutathione to reduce it to 2-GSH. So this is going to be oxidized, and then this will go back to the reduced form. And NADPH plus a hydrogen ion plays a role in this process. There are other enzymes that selenium is going to be a part of. So these are additional antioxidant enzymes. So we see that it is selenoprotein P. Selenoprotein P also has an antioxidant role, and we see that it can contain up to 10 selenocysteine residues. So this is a selenium-dependent antioxidant enzyme, but containing this form, the selenocysteine. We see that it has an antioxidant role by removing this peroxynitrite radical, and that radical is synthesized by white blood cells from superoxide radicals and nitrogen monoxide. So it removes this peroxynitrite radical. There's an additional antioxidant enzyme that selenium will play a role in. So we see it's this thioredoxin reductase. Again, this is an antioxidant enzyme. It works with NADPH. This also contains selenocysteine, and it reduces the oxidized thioredoxin, glutaredoxin, and transcription factors, receptors, and enzymes. So we'll see that it's going to be involved in reducing the oxidized thioredoxin, glutaredoxin and then these other factors, and therefore is involved in regulating cell growth, apoptosis, and intracellular signaling cascades. So a key factor here is it also contains the selenocysteine and is another antioxidant enzyme dependent on selenium. Also, we have the selenoprotein R. It is also an antioxidant enzyme, part of a group of methionine sulfoxide reductases, also containing the selenocysteine. And we see that it reduces the oxidation of methionine residues. So this is reducing the oxidation of methionine residues as a class of these methionine sulfoxide reductases. We also see, interestingly, that selenium plays a role in thyroid hormone synthesis. So we have these two thyroid hormones. We have first T4, or thyroxine, and we have T3, or the triiodothyronine. And we see that selenium is a part of this enzyme involved in converting T4 to T3, and it does this by catalyzing the removal of iodine from the 5 position of T4, converting it to T3, and then we are able to have the active form of T3, which can then enter circulation and be active in the body for various different roles that the thyroid hormone will be involved in. So here we see the RDA for selenium in adults for men and women. The RDA is 55 micrograms per day, and we see that it's slightly higher in pregnancy and lactation.